Welcome back, my friend. Before tonight's story begins, take a quiet moment for yourself. Now, settle in, get comfortable, and let tonight's quiet journey begin. There are places on Earth where sunlight has never arrived. Places so deep, so crushed by pressure that for centuries we assumed nothing could live there. And yet, at the bottom of the ocean, the sea floor breaks open, and from those wounds, the Earth releases black clouds, hotter than fire, like underwater chimneys, burning in darkness. And around them, entire cities of strange living things wait in the dark. Tonight, we go there. But none of that was known in 1977 when a small submersible called DSV Alvin descended along the Galápagos Rift. The crew expected bare volcanic rock, silence, maybe a few fish. Instead, their lights found towering black structures pouring smoke into the seafloor. Then, movement, white creatures waving slowly in water that should have killed them. And in that moment, human beings realized the deep ocean had been hiding another world. The Galápagos Rift Expedition, 1977. Long before anyone saw a hydrothermal vent, the deep ocean floor was imagined as a quiet and nearly empty place. Scientists understood that the seafloor spread slowly along great underwater ridges where molten rock rose from within the earth and formed new crust. They knew these fractures existed. They knew heat escaped from below, but no one understood what might gather there. In most scientific thinking, life depended on sunlight. That seemed almost beyond dispute. Plants captured light. Small creatures fed on plants. Larger creatures fed on them. Even the deepest animals, it was assumed, survived only because fragments of organic matter drifted down from the surface above like a slow marine snowfall. Everything in the end seemed connected to the sun. And so, when researchers prepared for an expedition to the Galápagos Rift in 1977, they were not expecting to challenge one of biology's deepest assumptions. They were looking mainly for geology. The expedition centered around DSV Alvin, a small research submersible already known for deep dives. Though few imagined this descent would become historic, Alvin was not large. Its pressure sphere was cramped. Instruments filled much of the interior. There was little room to move, only enough room to watch. As the submersible descended into the Pacific, daylight disappeared almost immediately. Blue gave way to black. The ocean outside the viewing ports became featureless, then colder, then silent, in a way difficult to describe. Hours passed in descent. Above them, the surface world continued with wind, weather, and sun. Below, another environment waited. One defined by pressure so immense it pressed against every inch of the submersible's hull. Nearly 2,500 meters down, Alvin approached the seafloor. Its lights reached outward. Basalt, broken lava, scattered sediment. At first, much as expected, but then something strange appeared. The instruments began detecting unusual temperatures, slightly elevated, then more. Warm water in the deep ocean was not impossible. But here, near a spreading ridge, it suggested something active, something moving through the earth. The pilots guided Alvin closer, and then they saw it. At first, It did not look like a chimney. It looked almost like shimmering water, a distortion like heat above pavement on a summer road, fluid rising from the seafloor, not imagined, not theoretical, visible, real. And then the lights moved farther and illuminated life, not scattered animals, not a few opportunistic creatures, communities, dense clusters, white clams, mussels, and towering red-tipped tube worms, unlike anything most people had ever imagined living in darkness. These were not organisms barely surviving. They were thriving. That may have been the most unsettling part. Abundance where scarcity had been expected. Life where theory suggested little should exist. Some of the scientists reportedly struggled at first to understand what they were seeing. The discovery did not fit existing assumptions. How could large communities survive here? There was no sunlight, no plants, no ordinary food chain, and yet the evidence stood in the beam of Alvin's lights. The answer would begin emerging in the years that followed. Bacteria, invisible but foundational. Microbes drawing energy, not from sunlight, but from chemicals rising in vent fluids, hydrogen sulfide, minerals, heat, a process that would become widely known as chemosynthesis. Not life powered by the sun, life powered by the earth itself. It is difficult now, decades later, to recover how disruptive that realization was. But imagine discovering an entire rule of biology had exceptions. Imagine descending in search of rock and finding another logic for life. That is close to what happened. Even the tube worms themselves seemed almost impossible. Many lacked ordinary digestive systems. They lived through symbiosis with internal bacteria. Their bodies were not operating according to expectations formed by familiar animals on land. They belonged to a world few had suspected, and there, in darkness older than human memory, they had been waiting. Some later compared the discovery to finding an oasis in a desert. Others called it one of the great biological discoveries of the 20th century. Both may be true, and in the quiet inside Alvin, during those first moments, it was probably simpler than that. Surprise, silence, and perhaps disbelief, because sometimes discovery does not arrive as triumph. Sometimes it arrives as stillness, as people staring through a small window, trying to understand whether what they are seeing can be real. The Galápagos Rift expedition did not only reveal hydrothermal vents, it altered geology, biology, and later, even thinking about life beyond Earth. If life could flourish here around heat rising from a fractured seafloor, then perhaps oceans hidden beneath ice on distant worlds might not be empty either. Ideas about places like Europa would eventually draw strength from moments that began here. But all of that came later. On that dive, none of those implications yet existed. There was only the seafloor, dark chimneys beginning to form, warm fluid rising through cracks in young ocean crust, and strange living towers swaying in black water. The earth, it seemed, was not silent below. It was breathing. And in 1977, for the first time, human beings watched it breathe. Black smokers. After the first astonishment of discovery came another question. What exactly were these structures? Those dark towers rising from the seafloor. What were they made of? And why did they seem, from a distance, to be smoking? The phrase black smoker did not exist at first as something familiar. It emerged because scientists needed a name for something that looked almost industrial, yet was entirely natural. At great depth, seawater does not simply rest upon the ocean floor. In some places, it enters cracks in the Earth's crust. It sinks downward through fractured rock, sometimes kilometers below the seafloor. There, close to underlying magma, the water encounters enormous heat, not warm, not merely hot, extreme heat. In some vent systems, fluids can exceed 350 degrees Celsius. In some cases, even approach 400, temperatures that seem impossible to associate with ocean water. And yet, under the immense pressures of the deep sea, that water does not boil in the way it would at the surface. This was one of the strange lessons hydrothermal vents taught. Pressure changes behavior at these depths. Water can remain liquid under conditions that would otherwise turn it violently to steam. And in that superheated state, it changes. It reacts chemically with surrounding rock. It dissolves metals. It absorbs minerals. It becomes something far more than seawater. Then, driven upward, it rises back toward the seafloor, and where it escapes through vents, it meets the near-freezing ocean around it. There is a collision, heat meeting cold, dissolved minerals suddenly precipitating, and in that instant, what looks like smoke appears. But it is not smoke, not in the ordinary sense. It is a storm of mineral particles, dark clouds, rich in metal sulfides, iron, copper, zinc, sometimes more. These particles pour into the water column, swirling upward like soot from a chimney. And so they were called black smokers. The chimneys themselves grow slowly, not carved, built layer by layer. Mineral deposits accumulating as vent fluids continue escaping. Over time, small openings can become towers, some rising several meters, some far taller, fragile in places, massive in others, like underwater cathedrals, formed not by hands, but by chemistry. And these structures are not permanent. Some grow, some crack, some collapse, some become extinct, because black smokers are tied to the restless movement of Earth itself. They belong to tectonic places that shift, stretch, break, renew. There was something unsettling for scientists in realizing that the ocean floor was not the static landscape many had imagined. It was active, dynamic, almost architectural. The Earth was constructing chimneys in darkness, and through them, circulating heat from its own interior. This also transformed geology, because hydrothermal circulation turned out to be far more important than previously understood. These vents were not curiosities. They were part of how the planet releases heat, part of how ocean crust is altered, part of how elements move through Earth's systems, a hidden engine operating continuously, mostly unseen. Some researchers began to think of mid-ocean ridges less as submerged mountain chains and more as living boundaries, places where Earth was constantly being made, and vent fields became windows into that process. Yet, for all their scientific importance, black smokers also carried something almost mythic in appearance. To descend through black water and see dark plumes rising from jagged towers, lit only by submersible lamps, was to witness something that seemed closer to another planet than to familiar Earth. Many later said the scenes looked alien. Some compared them to industrial ruins, others to underwater volcanoes exhaling smoke. But perhaps what made them unforgettable was contradiction. They looked violent, yet sustained life. They emerged from fractures, yet built structures. They released toxic chemistry, yet nourished ecosystems. Everything about them seemed to invert expectation. Even danger carried limits not immediately obvious. Move too near certain vent openings, and temperatures could become lethal. Move too far, and life thinned. Many organisms at vents lived within narrow boundaries, a precise negotiation between freezing seawater and near scalding fluid, between survival and death, all around a chimney. That too astonished researchers. Life was not merely present. It was arranged around gradients, heat, chemistry, flow, as if entire ecosystems were shaped by invisible contours only their inhabitants could sense. And still, there were deeper questions. How long had black smokers existed? Millions of years? Longer? Had they shaped ancient oceans? Had they influenced early chemistry on Earth? Could something like this have existed before complex life ever appeared? Questions widened. The chimneys led outward into philosophy almost as much as science, because once you see the Earth venting heat into darkness, building towers of metal, and feeding life without sunlight, you begin to realize the planet may be stranger than human imagination first allowed, and perhaps older in its mysteries. For the crews who first watched black plumes rising from those chimneys, there may also have been a quieter realization. The deep ocean was not empty wilderness. It contained processes still operating beyond ordinary human sight. Ancient processes still making structures, still circulating minerals, still breathing through fractures. And in the darkness of the seafloor, those black smokers kept rising like the slow, visible breath of the earth below. Life built on chemistry. For generations, one idea had seemed almost immovable. Life depends on sunlight. Not every creature must touch the sun directly, of course, but somewhere at the beginning of the chain, sunlight had to enter. That was the rule, or so it appeared. Yet around hydrothermal vents, that rule began to loosen, then fracture, then perhaps become something larger. Because scientists looking at those dense communities surrounding black smokers faced a question even stranger than the chimneys themselves. What feeds all this life? There were giant clams, dense mussel beds, fields of tube worms, crabs moving through mineral-coated rocks, shrimp gathering near shimmering hot water. Something sustained them. But what? No sunlight reached these depths. No green plants grew here. No ordinary photosynthesis. And so researchers began tracing the answer downward to organisms too small to see. Bacteria. At first glance, it may have seemed almost disappointing that the great mystery might begin with micro, but in truth, it made the discovery even more extraordinary, because these microbes were doing something thought possible in theory, yet never understood at this scale. They were drawing energy, not from light, but from chemistry, specifically from compounds emerging in hydrothermal fluids. Hydrogen sulfide, a chemical many surface organisms experience as toxic, something associated in ordinary human experience with decay. And yet here it was fuel. These bacteria oxidized those chemicals, and from that process generated energy, using that energy to build organic matter to support life, a kind of primary production, not photosynthesis, chemosynthesis. The word sounds almost technical, but its meaning was profound. Life powered by earth chemistry, not sunlight, not surface conditions, something different. And once that idea became clear, the vent communities began to look different too. They were not anomalies. They were ecosystems, complete systems rooted in microbial energy. The giant tube worms became perhaps the most famous example. Riftia pachyptela looked almost impossible, even before scientists understood how they lived. Red plumes extending upward, white bodies anchored in protective tubes, no mouth, no stomach, no intestines. How could such an animal survive? The answer was almost difficult to believe. It lived in partnership. Inside its body, an organ packed with symbiotic bacteria. The worm supplied chemicals the bacteria needed. The bacteria produced nourishment, host and microbe, not separate strategies, but one shared system, a collaboration so intimate the animal itself could not live without it. There was something quietly radical in this. Life here was not merely adapting to harsh conditions. It was reorganizing relationships, building survival through alliances. Surface biology had rarely imagined at such scale. Even the blood of these worms drew attention. It carried oxygen, but also transported sulfide, a chemical dangerous to many forms of life. Their biology seemed tuned to a world built on chemistry most creatures avoid, as if evolution in darkness had written different solutions, and tube worms were only part of it. Vent clams carried microbial partners too, some mussels. Other organisms relied more indirectly on this microbial foundation. Predators fed on grazers, scavengers moved among them, food webs emerged, all built, ultimately, on bacteria drawing energy from Earth's interior. Try to imagine what that meant for those who first grasped it. An entire ecosystem rooted not in sunlight from above, but in geochemical energy rising from below. It did not merely add a new category to biology, it expanded what habitable could mean. Places once assumed barren might not be barren at all, and the implications kept widening. If life could organize around chemical disequilibrium at hydrothermal vents, what other environments might support it? Underground? Beneath ice? Within hidden oceans? Thoughts of worlds like Europa began to feel less speculative, because Earth itself had already revealed a precedent. The impossible had become an example. Yet perhaps the deepest shift was philosophical. Sunlight had long held almost symbolic status as origin, as source, as beginning. But hydrothermal vents suggested life might arise from darkness too, from gradients, from rock-water reactions, from heat, from chemistry. That possibility unsettled more than scientific models. It touched older human assumptions about what life is and where it belongs. Some scientists even began revisiting origin of life questions through this lens. Could ancient vent-like systems have helped early life emerge? Could chemistry like this have preceded biology itself? Those debates would continue. They still do. But they began, in part, because of what researchers saw surrounding vent chimneys and what bacteria were doing there unseen. There is something almost humbling in it. The creatures the human eye cannot perceive may sustain entire worlds. That invisible processes may be more foundational than visible ones, and that beneath miles of dark water, life had been conducting this chemistry long before human beings learned the word for it. The black smokers rose, the bacteria fed, the tube worms swayed in currents, and in silence, an old belief slowly changed. Life did not depend only on what falls from the sun. Sometimes it rises from the earth. The theory of life's origin changes. Once scientists accepted that hydrothermal vents supported life independent of sunlight, another question rose almost immediately, not about what lives there now, but about beginnings. Could places like this have something to do with how life began at all? For a long time, theories about life's origin often lean toward shallower worlds, warm ponds, tidal pools, sunlit chemistry, lightning crossing primitive skies. Ideas varied, sometimes sharply, but many shared an assumption that early life emerged in environments influenced directly or indirectly by the surface. Hydrothermal vents complicated that because they offered something unusual, not simply energy, but persistent energy, continuous gradients, heat, minerals, flow, boundaries, where chemistry was always being driven out of equilibrium. And life, as many scientists understood it, depends in part on disequilibrium, on differences in concentration, in charge, in temperature, in chemical opportunity. Vents seemed full of such differences, almost designed, some thought, for reactions, especially if one tried imagining the young Earth, a planet more volcanic, more unstable, oceans interacting with a hotter crust, perhaps many more hydrothermal systems than today, perhaps countless hidden places where water and rock met under extreme conditions. To some researchers, that no longer seemed like background. It began to look like possibility. One influential idea centered on mineral structures, tiny pores, microscopic compartments within vent minerals, natural chambers where molecules might concentrate rather than disperse into vast oceans, a place where chemistry could be held long enough to become more complicated, then perhaps more organized, then perhaps something approaching metabolism or inheritance, not life yet, but movement toward life. There was a quiet elegance to this, that the earth itself might have built tiny chemical laboratories long before cells existed. Another idea focused on proton gradients, differences in chemical conditions across boundaries, something strikingly reminiscent of processes modern cells still use, as if ancient geology and present biology might share echoes. That possibility fascinated many, though not everyone agreed, and they still do not, because origin of life research remains filled with debate. Questions remain immense, evidence indirect, arguments often competing. Some still favor surface-associated scenarios. Some favor hybrid models. Some see vents, especially alkaline systems, like those later associated with places such as Lost City Hydrothermal Field, as especially compelling. Others remain cautious. Science rarely moves by certainty alone, but hydrothermal vents changed the discussion. That much is difficult to deny. They made deep ocean origin scenarios serious, not speculative fantasy, serious science. And once that door opened, another door often followed. If life might begin in dark ocean worlds around hydrothermal activity, what about elsewhere? The thought seemed almost inevitable. What about icy moons with hidden oceans? What about Europa? What about Enceladus, where plumes later hinted at water, chemistry, perhaps hydrothermal interactions below? Could oceans no human has seen hold vents no human has touched? And if so, could they hold life? Questions that once belonged largely to imagination began entering planetary science. Astrobiology itself was shaped by such possibilities. In a strange way, chimneys on Earth's seafloor reached outward into thinking about worlds beyond Earth. That may be one reason hydrothermal vents continue to hold such fascination. They are not only ecosystems, they are mirrors held toward beginnings and perhaps toward elsewhere. Yet there is also something more intimate in this shift, because ideas about life's origin are never only technical. They touch a deeper human instinct, the desire to ask, where did we come from? How did living matter cross the threshold into life? Why is there something alive here at all? Hydrothermal vents did not answer those questions, but they made them stranger and in some ways richer. They suggested life may not have emerged in bright places alone, not only under open skies, but perhaps in hidden fractures, in darkness, amid minerals and heat, with no witness, no sunlight, only chemistry becoming more than chemistry. There is something almost poetic in that possibility. That life may have begun not in a dramatic flash, but in slow persistence, in gradients sustained over time, in molecules meeting again and again until something held, until something copied, until something endured. And maybe that is why, even beyond laboratories and theory papers, hydrothermal vents continue to stir imagination, because they suggest the Earth has been conducting experiments for billions of years, still conducting them far below waves, far below memory. The chimneys rise, minerals circulate, hot water moves through fractured rock, and perhaps in places like these, long before animals, long before oceans held fish, long before anything looked back at the stars, the first small steps toward life may have already begun. And if that is even partly true, then at the bottom of the ocean, human beings did not only discover strange creatures, they may have glimpsed an echo of their own beginning. The East Pacific Rise expeditions. By the late 1970s, the first discoveries at the Galápagos Rift had already unsettled science. Hydrothermal vents were real. Black smokers were real. Entire ecosystems built on chemistry were real. But one question remained open. Was this unusual or widespread? Were the vents near the Galápagos Rift rare exceptions, or only the first glimpse of something much larger? That question pulled researchers back to sea, and it led them toward another immense underwater boundary, the East Pacific Rise. If the Galápagos Rift had opened a door, the East Pacific Rise would widen it, because this was not a quiet or geologically modest region. It was one of the fastest spreading mid-ocean ridges on Earth, a place where tectonic plates moved apart rapidly, where new crust formed, where heat flowed upward, and where some suspected hydrothermal activity might be even more intense. Expeditions returned with submersibles, with instruments, with growing expectations. But even then, what they found often exceeded them. The vent fields here were not simply repeats of earlier discoveries. In some places, they seemed more dramatic. Taller chimneys, denser vent communities, more vigorous fluid discharge, a seafloor that looked, at moments, almost restless, as if Earth's internal processes stood closer to the surface. And there was something else. Temperature measurements pushed understanding further. Vent fluids reached astonishing extremes, far hotter than ordinary imagination associates with ocean water, more than 350 degrees Celsius, in some cases near 400, and still remaining liquid under crushing pressure. The lesson deepened. The deep ocean was not merely cold darkness. It contained thermal violence hidden within it, and life had arranged itself around that violence. Some vent fields looked almost like clustered cities, chimneys rising near one another, plumes drifting upward, tube worms massed in pale red forests. Riftia pachiptila appeared again, often in remarkable abundance. Their presence itself became a kind of sign. Where they gathered, there was chemical opportunity, there was flow, there was a vent system alive. Researchers began seeing patterns, connections. Hydrothermal systems were not isolated curiosities. They appeared linked to broader ridge processes, to plate motion, to volcanism, to the architecture of ocean crust. And that changed the scale of thinking. The question was no longer, can hydrothermal vents exist? It became, how much of Earth operates this way without us seeing it? That is a different kind of question, a planetary question. Some estimates suggested enormous quantities of seawater may circulate through ocean crust over geologic time through such systems. If true, hydrothermal circulation was not marginal. It was fundamental, part of Earth's metabolism, one might almost say, though scientists would use more careful language. Still, the metaphor lingered, and the East Pacific rise reinforced another realization. Vent ecosystems were not static. They changed, sometimes rapidly. Some expeditions returned to sites already altered. Structures collapsed, new chimneys formed, communities shifted. The seafloor, once imagined almost motionless, behaved more like living terrain, temporary, eruptive, renewing. That unsettled old assumptions in a different way, because deep time and sudden change seem to coexist here. Processes millions of years old and changes overnight. Some of the most striking moments came when researchers began documenting seafloor volcanic events associated with ridge activity, fresh lava flows, buried vent communities, then later new colonization, life returning, as if destruction and beginning cycled together below. There was something almost sobering in watching that. The vent worlds were not permanent refuges. They were unstable. Organisms there often lived in landscapes subject to disappearance, and still they flourished. That fact fascinated evolutionary biologists. How does life adapt not only to extreme chemistry, but to instability itself? The East Pacific rise pushed such questions forward. It also strengthened links to broader ocean exploration, because each expedition made it harder to believe known vent fields were the full story. If they existed here, how many more lay undiscovered along the world's mid-ocean ridges? The answer, even now, is incomplete. Many remain unmapped, some unseen, perhaps many. And so the East Pacific Rise was more than a second chapter. After the Galápagos Rift, it was confirmation, expansion, and in some ways, escalation. The Earth below was proving even stranger than first imagined. Not one hidden vent field, but networks, not isolated anomalies, but systems, not a single astonishing discovery, but a hidden planetary process. And for those descending again in submersibles through black water, watching chimneys appear in the lights, watching dark plumes rise, watching living communities gather around heat emerging from fractures, there must have been a growing feeling difficult to ignore. This was not a rare exception. This was part of how the world worked, quietly, unseen, all along. And across the East Pacific Rise, the Earth kept opening, kept venting, kept building chimneys in darkness, and human beings, only just beginning to notice, followed those rising black plumes deeper into the mystery. Lost City, 2000. By the time the 20th century was nearing its end, hydrothermal vents had already transformed science. Black smokers had become almost iconic. Dark chimneys, superheated fluids, metal-rich plumes. Life gathered at the edge of heat. And yet, even then, many assumed they understood what a hydrothermal vent was supposed to be. They expected fire beneath water, volcanic influence, sulfur-rich chemistry, black smoke. That was the pattern. Then, in 2000, another discovery disturbed the pattern again, and it began, as such discoveries often do, with exploration in a place few people had heard of. Along the mid-Atlantic ridge, scientists investigating a massif west of the ridge axis encountered something unexpected. Not black chimneys, not smoke, dark plumes, but pale towers, white structures rising from the seafloor. Some delicate, some monumental, some taller than buildings. A vent field unlike anything previously known. It would be called Lost City Hydrothermal Field, and the name somehow fit because it looked, in the lights of submersibles, almost architectural. Ruins, spires, silent mineral towers, standing in deep water, but appearance was only the beginning. Its chemistry was stranger still. Unlike black smokers, driven strongly by magmatic heat, Lost City appeared tied largely to a different process, rock reacting with seawater, a process called serpentinization, water entering ultramafic rocks, chemical transformations, releasing heat, producing hydrogen, methane, alkaline fluids, a very different geochemical world. And unlike black smokers with fluids reaching extraordinary temperatures, Lost City's vent fluids were much cooler. Though cooler in this context can be misleading, still hot, but often around ranges far below classic black smoker extremes. Yet, life existed here too, and chemistry here fascinated origin of life researchers, perhaps even more, because some saw in Lost City something potentially ancient in character, conditions that might resemble environments on the early Earth, long-lived systems, stable chemical gradients, hydrogen availability, natural mineral structures. For some, this seemed almost a model, a possible bridge between geology and prebiotic chemistry, though debate continued, as it still does. But what startled many at the time was simpler. Hydrothermal vents had turned out not to be one kind of thing. There were multiple kinds. The deep earth was offering different pathways, different chemistries, different architectures. The category itself had widened, and that widened imagination, because if black smokers had suggested one kind of hidden world, Lost City suggested another, quieter, perhaps, but in some ways more mysterious. There was also something haunting in its scale. Some carbonate towers rose to extraordinary heights, structures sometimes compared to ancient monuments, formed not over human history, but through ongoing mineral precipitation, slow construction in darkness. The earth building towers again, but this time white, pale against black water, almost ghost-like. Some researchers later described the place with an emotional tone, unusual in technical science, beautiful, otherworldly, even eerie, because the site did not merely feel geologically interesting. It felt improbable, as if found rather than expected, as if one had stumbled into something the ocean had been keeping. And unlike many vent systems associated with more transient volcanic activity, Lost City appeared potentially long-lived, perhaps active on timescales far beyond many classic vent fields. That mattered because persistence matters in origin scenarios. Time matters. Chemistry may need time. Gradients may need time. And so this discovery fed not only marine geology, but some of the deepest questions science asks. How does life begin? What environments sustain first steps? What planetary conditions matter most? Some looked toward Earth's past. Others looked outward again, toward Europa and Enceladus, because if serpentinization-driven systems might exist elsewhere, perhaps something like Lost City was not unique to Earth. And if not unique, what might that imply? Questions widened once more, as they often do in ocean exploration. A dive meant to study geology becomes a question about life in the universe. That has happened more than once in this story, and perhaps nowhere more quietly than here, in a field called Lost City, where pale chimneys vented hydrogen-rich fluids into darkness, where the earth seemed to be conducting chemistry in slow silence, where assumptions once again had to be loosened. First, hydrothermal vents had overturned the idea that life depends entirely on sunlight. Now Lost City helped challenge the idea that hydrothermal vents themselves fit a single model. The mystery had become layered, deeper, and perhaps harder to contain, because every time scientists thought they had found the boundary of what the deep ocean could do, the ocean moved the boundary farther. And in the black Atlantic, those pale towers kept rising, still venting, still building, still standing in darkness, like a city no human civilization made, and perhaps one of the oldest kinds of places Earth ever knew. Life at 400 cc. There is a number that returns often in discussions of hydrothermal vents: 400 degrees Celsius, sometimes a little less, sometimes near it, sometimes cited with caution, because vent conditions vary. But the number lingers because It sounds impossible. At that temperature, human intuition resists. How could anything associated with life exist near water that hot? How could living organisms remain anywhere close to it? At first glance, it seems absurd, but hydrothermal vents have a way of forcing a second look. The first thing scientists learned was this: life is not living inside 400-degree vent fluid, as though such temperatures are ordinary habitat. That would be a misunderstanding. The hottest vent fluids themselves can exceed limits many organisms tolerate. But what matters is not only the vent opening, it is the gradient, that narrow and shifting zone where superheated fluids mix with cold seawater, where extremes soften into possibilities and life gathers there, at boundaries, at edges, at places between lethal conditions. That is where much of the mystery lives. Some organisms position themselves astonishingly close to danger. Vent shrimp, including Rimicaris exoculata, have been observed clustering near vent flows in ways that once seemed unimaginable. They do not sit in uniform heat. They occupy fluctuating environments, moving within gradients, tracking conditions, living in narrow margins. A few centimeters can matter. Temperature can change sharply across very small distances, and in those differences, life negotiates survival. That alone was extraordinary, but microbes pushed the question even further, because some extremophile microorganisms, hyperthermophiles, proved capable of tolerating temperatures once thought incompatible with life. Not 400 degrees, but still astonishingly high, above boiling temperatures familiar at the surface, made possible because pressure changes everything. And these microbes did more than survive. They functioned, they metabolized, they reproduced, they made too hot for life harder to define. That phrase began to erode, because where exactly is the upper thermal limit? Scientists tested, argued, revised, raised thresholds, sometimes cautiously, sometimes dramatically. The boundary kept moving, and every time it moved, so did the idea of habitability that mattered beyond marine biology. Because if life can persist in hotter, harsher conditions than once believed, then environments dismissed elsewhere might deserve reconsideration too. Again, the deep ocean was changing more than ocean science. It was changing possibility. Still, heat was never the only challenge. Vent organisms face chemistry as well. Hydrogen sulfide, heavy metals, acidity in some settings, instability, pressure immense enough to crush ordinary structures. And yet, adaptation emerged. Proteins evolved to remain stable at higher temperatures. Membranes adjusted. Biochemistry found ways surface organisms often do not need. Evolution, once again, had written solutions in darkness. There is something almost philosophical in that life does not merely occupy safe places. It explores margins, presses boundaries, finds footholds where conditions seem nearly prohibitive. At hydrothermal vents, that truth feels visible, almost literal. Creatures living where cold and near scalding waters meet, microbes living near thresholds long thought impossible, entire ecosystems arranged around unstable edges. It can feel less like ordinary habitat and more like life negotiating with extremes. And yet scientists also learned caution. Stories about life at 400 cc can mislead when simplified. The reality is subtler. Life is associated with systems where such temperatures may occur. Life exploits gradients shaped by them. Life may approach extraordinary thermal limits, but the hottest fluids themselves are not simply crowded with complex animals swimming through 400-degree water. The truth is more interesting than myth because it is about boundaries and how close life can move toward them. That is often where science becomes most compelling, not in exaggeration, but in the precision of what survives where. Some researchers came to see hydrothermal vents as laboratories for testing the resilience of biology itself. What is the upper limit of heat, of pressure, of chemical stress? What is essential? What is flexible? What can evolution reinvent? Questions that began with vent microbes reached far, even into origins research, because some wondered whether high-temperature environments may preserve clues to early biochemical possibilities, or whether ancient life itself may have passed through such extremes. The debates remain, but the questions persist, and perhaps that is part of what makes this subject so enduring. The vents did not simply reveal strange creatures. They made limits uncertain, and once limits become uncertain, wonder returns. Far below the surface, near fractures, where water heated by earth rises through darkness, there are places where temperatures approach what once seemed incompatible with life. And still, around those gradients, microbes feed, shrimp gather, ecosystems hold, not because life ignores danger, but because somehow it has learned to live beside it. When vents die, for a time, early descriptions of hydrothermal vents carried an impression of permanence. Chimneys rising, fluids flowing, tube worms swaying, dark plumes climbing into black water. It was easy, perhaps, to imagine these places as fixed, ancient, steady, always there. But the deeper scientists looked, the less permanent they seemed, because hydrothermal vents do not only begin, they end. And that changed how people understood vent ecosystems. They were not simply extreme habitats. They were temporary worlds, born, active, and sometimes gone. A vent may weaken when underground pathways shift. A fracture may seal. Fluid flow may diminish. Heat sources may migrate. Volcanic events may bury entire fields beneath fresh lava. A chimney may collapse under its own mineral weight. What looks monumental in one decade may be broken rubble in another. Sometimes, sooner, the earth builds and the earth dismantles, often in silence, for the organisms living there. This is not abstract geology. It is survival, because when a vent dies, chemistry changes, flow weakens, the energy base falters, and the ecosystem feels it. Tube worms may perish, microbial communities shift, species dependent on active vent chemistry may disappear from that site. A living community can become, in time, a mineral graveyard. That realization altered marine biology profoundly because it introduced something once underappreciated. Vent ecosystems have life cycles. They are not static assemblages. They pass through stages: colonization, growth, disturbance, decline, sometimes renewal, almost ecological succession in darkness. And with that became another question. If vent fields are temporary, how do species persist at all? The answer led to one of the most elegant ideas in deep-sea ecology: connectivity. Some organisms disperse, larvae drifting through deep currents, searching, in a sense, for new vents, new openings, new chemical refuges. One vent field may die, another may awaken, and species survive by moving across a hidden network of temporary worlds, like islands, but islands of chemistry, separated in darkness, linked by dispersal. It was a beautiful idea and a sobering one, because it meant survival may depend not only on one vent, but on many, on pathways between them, on unseen connections. Destroy enough of those connections, and resilience may weaken. That realization would matter later in debates over deep-sea mining. But even before such debates, the biology itself was astonishing. Imagine living in a world where your habitat may vanish under lava, where the ground beneath you may erupt, where survival depends on descendants finding another hidden oasis hundreds of kilometers away. And yet, life persists. That is not merely adaptation, it is endurance, written across a fractured planet. Some of the most dramatic evidence came when scientists revisited vent sites after volcanic events. Places once full of organisms, buried, changed, gone. Then later, new colonists appearing, life returning, different at first, then richer, recovery. There was something almost moving in that, because destruction was not always final. Sometimes it became beginning. The death of a vent could open ecological succession elsewhere. A closed chimney here, a new fracture there, an ending folded into renewal. That rhythm made hydrothermal systems feel almost less like isolated features and more like processes. Breathing systems, opening and closing over time. Some vents may persist long, others may be brief. Some vanish abruptly, some fade. There is no single story, only patterns of impermanence. And perhaps that too reshaped scientific imagination, because the deep ocean floor had often been imagined as a realm of slowness, stillness, geologic patience. But hydrothermal systems revealed something more restless, places where sudden change and long duration coexist, where catastrophe and colonization are neighbors, where life lives with instability as ordinary condition. That has philosophical weight too, because humans often associate thriving with stability, yet vent organisms suggest another possibility. Thriving sometimes includes learning to endure unstable worlds. That idea feels larger than marine biology. Far below sunlight, a black smoker may weaken, its plume may thin, its chimney may fracture and fall. The chemical gradients that fed a living community may dissolve into cold seawater. Silence may return, at least for a while, and yet elsewhere, perhaps along another unseen ridge, another fracture opens, another vent begins. Hot fluid rises, minerals precipitate, a chimney starts forming in darkness, and drifting larvae carried through the deep may find it, which is why a dying vent is not always only death. Sometimes it is a passage, one hidden world closing, so another far away in the dark can begin. Giant tube worm forests. Among all the creatures discovered at hydrothermal vents. None seem to linger in human imagination quite like the giant tube worms, perhaps because they looked so improbable, perhaps because they seemed, even to scientists, almost designed for another world, or perhaps because in the beams of deep submergence lights, they did not appear as scattered animals. They appeared as landscapes, forests, living fields, rising from the seafloor. At first glance, Riftia pachytyla can seem almost simple. A pale, tubular body, a vivid red plume extending from the top. No face, no eyes, no obvious signs of the familiar animal world. And yet this simplicity is deceptive because these organisms are among the strangest large animals ever studied. Some can grow over 2 meters long in a place where food, by ordinary logic, should scarcely exist. That alone is remarkable. But size is only part of the mystery. It is how they live that unsettles expectation. As researchers discovered, adult giant tube worms have no mouth, no stomach, no intestines. An animal, apparently without a digestive system, and still alive, still growing, still thriving in dense colonies. How? The answer, as in so much vent biology, lies in partnership. Inside the worm is a specialized organ, often called the trophosome, packed with symbiotic bacteria, vast numbers of them. These microbes perform chemosynthesis using chemical energy from vent-derived compounds, producing nourishment. The worm, in turn, supplies what the bacteria need, a living alliance, not incidental, essential, host and microbe functioning almost as one. There is something almost difficult to absorb in that. A large animal built around internal bacteria, an organism whose way of feeding is not feeding in the ordinary sense, but cooperation. It feels less like an exception, more like a reminder that evolution can invent strategies stranger than imagination. Even the red plumes fascinated researchers. Their color comes partly from specialized hemoglobin, and not ordinary hemoglobin alone. This chemistry helps transport oxygen and, crucially, compounds like sulfide, chemicals dangerous to many organisms. What would poison some forms of life becomes part of survival here. Again and again, vent biology seemed to invert familiar rule. Danger becoming resource, toxicity becoming fuel. Tube worms often cluster where conditions are neither too cold nor too close to lethal vent discharge. They occupy gradients like so much at vents, not random placement, but ecological positioning, a kind of living geometry around chemistry seen from submersibles. Dense colonies can appear almost like underwater meadows, thousands swaying slowly in currents, red plumes extending and withdrawing, movement so gentle that some observers describe scenes as almost serene, though they existed beside some of the harshest conditions on Earth. That contrast made them unforgettable. Beauty beside extremity, stillness beside geological unrest. And there was another surprise: growth rates. Some studies suggested giant tube worms can grow astonishingly fast, far faster than many would expect for deep-sea organisms, especially in environments once assumed energy poor. That challenged yet another assumption. The deep sea was not always slow in the ways people imagined. Where chemical energy surged, life could respond vigorously. rapidly, even abundantly. Some scientists came to think of tube worm colonies almost as ecological engineers, their physical presence shaping microhabitats, influencing local conditions, providing structure around which communities gather, not merely inhabitants, participants in the architecture of vent ecosystems, and yet they remain vulnerable. If vent chemistry changes, if flow weakens, if eruptions bury habitat, colonies may die. Their towering fields can vanish. Another reminder that these strange forests belong to temporary worlds, born where Earth opens, gone when Earth closes. That fragility somehow makes them more extraordinary, not less, because they are not relics surviving unchanged. They are living responses to unstable places. Evolution written in motion. It is perhaps no surprise they became icons of hydrothermal research. For many people, giant tube worms were the image that made the deep ocean newly strange, newly alive. They made hydrothermal vents visible in the imagination, no longer just geology, but inhabited worlds. And still, they continue to raise quiet questions. Why did evolution take this path here? How many other symbioses remain unknown in deep oceans? Could analogues exist elsewhere? If hydrothermal systems exist beyond Earth, again the mind drifts outward, as it often does in this story. Because once you see forests of animals thriving without sunlight, fed by bacteria within their own bodies, growing around heat, rising from fractured crust, it becomes harder to speak casually about what life can or cannot be. Definitions loosen, wonder return. Far below the surface, where black smokers vent into darkness, those pale towers of living worms still rise, thousands together, swaying in slow currents, fed by chemistry, rooted, in a sense, not in soil, but in the breathing earth below. And in the silent dark, they resemble something few expected to find at the bottom of the ocean: a forest. Blind crabs and ghost shrimp. If giant tube worms made hydrothermal vents seem almost like alien forests, other creatures made them feel stranger still. Because among chimneys and mineral towers, life did not only take root in stillness, it moved, scuttled, gathered, climbed over hot rock, crowded near shimmering water, and some of the creatures doing so seemed almost invented. White crabs with hair-like coverings, shrimp living where temperatures swing toward extremes, animals with little use for ordinary sight, creatures shaped once again by darkness. One of the most curious among them is Kiwa hirsuta. Its popular name alone carries a kind of myth, Yeti crab, as though science itself briefly borrowed folklore. And perhaps the name endured because the animal looked so improbable, pale, almost ghost-like, with bristle-covered claws and limbs that appeared furred, though the fur was not fur at all, but setae, hair-like structures, and on those structures, bacteria again, partnership again, chemistry entering biology. Some related species were later observed appearing almost to cultivate microbes on their bodies, an idea so strange it can sound metaphorical, but researchers took it seriously. Animals carrying bacterial growth as part of survival, as if even movement itself at vents had become entangled with microbial worlds. vents. And then there were the shrimp, particularly species like Rimicaris exoculata, masses of them sometimes gathering in astonishing density near vent openings, crowding surfaces in numbers that made rocks seem alive, living close to gradients many creatures would avoid, so close at times that scientists wondered how they managed it. Part of the answer lay in adaptation, part in behavior, part in sensing conditions humans barely perceive. Because in a world without sunlight, other ways of reading the environment matter. Some vent shrimp possess unusual light-sensitive structures, though not vision in familiar human terms, enough perhaps to detect faint thermal glow or environmental cues associated with vents. Even that remains part of a larger mystery. How do animals orient in such darkness? How do they navigate heat gradients? How do they avoid lethal zones centimeters away? Questions remain, and perhaps always partly will. There is something humbling in that even after discovery, life at vents often remains only partly understood. The crabs, too, challenged assumptions, not only because some appeared blind or reduced in ordinary visual dependence, but because blindness in darkness is not failure, it is economy. Why invest in eyes where light never comes? Evolution does not mourn unused designs. It repurposes, reduces, rebuilds, and so sensory worlds changed. Touch, chemistry, temperature, flow, a different language of survival. One humans can only partly imagine. Some researchers began speaking not just of vent organisms, but of vent sensory ecology, how creatures perceive a world of invisible gradients. That idea itself felt almost like entering another form of reality, because perhaps the vent world is structured by boundaries humans do not directly feel. Chemical landscapes, thermal contours, fields of information living bodies read continuously, and crabs and shrimp move through them as naturally as birds move through wind. There was also something oddly theatrical in how some appeared under submersible lights, white bodies against black rock, clouds of drifting particles, shrimp flickering at the edges of shimmering vent water, crabs climbing mineral towers. Scenes so unfamiliar, they often prompted comparisons to extraterrestrial worlds. And perhaps those comparisons persist for a reason. These creatures do not merely survive harsh places. They make harsh places seem inhabited in ways imagination struggles to anticipate. That matters because one of the deepest lessons of hydrothermal exploration has been this: the extreme is not always empty. Sometimes it is crowded, sometimes inventive, sometimes beautiful, even if beauty arrives wearing claws. Of course, not everything about these animals is fully known. Some behaviors remain debated, some relationships still studied. Science here is unfinished, and perhaps that too belongs in the story. The vents are not solved places, they are living questions. But what is already known is enough to alter perspective. Blind crabs carrying microbial associations, shrimp living near scalding gradients, animals perceiving a dark chemical world beyond ordinary human senses. None of this belonged to old expectations of the deep sea, and yet all of it was there, waiting long before humans descended to see it. Far below the sun, where black smokers rise through darkness, white crabs still move over mineral towers. Shrimp gather in dense, restless clusters. Invisible gradients shape every motion, and in that silent world, life does not merely endure. It adapts so completely that darkness itself becomes a homeland. Vent predators. For a time, early descriptions of hydrothermal vents focused on abundance: tube worms, clams, shrimp, crabs, dense communities arranged around chemistry. And there was a tendency, perhaps understandable, to imagine these places mainly as systems of microbial production and strange grazers. But wherever life gathers in abundance, something else usually follows. Predators, hunters, scavengers, the quiet pressure of being eaten. Hydrothermal vents were no exception, though even here, predation often took forms unfamiliar, less dramatic perhaps than human imagination expects, but no less real, because a vent field is not only a place where energy enters an ecosystem, it is a place where that energy moves from microbes to symbiotic animals, to grazers, to hunters. Food webs do not stop at wonder, they continue into appetite. Some predators are fish, species moving through vent regions, feeding opportunistically where life is concentrated. Others are crabs. Some are polychaete worms. Some are small, elusive hunters, difficult even to observe directly. And perhaps most intriguing, some predators may appear almost ordinary in form until one realizes where they live: near chimneys, venting near scalding fluids into darkness. Ordinary shapes, extraordinary settings. Vent crabs, including members associated with hydrothermal regions, sometimes feed not only as scavengers, but as active consumers. Shrimp may become prey, soft-bodied organisms, vulnerable. Carrion, when available, rarely goes unused, because in unstable systems, waste itself can be opportunity. That too is part of ecology. Nothing is merely present. Everything may be food. Some fish associated with vents, including L-pout-like species, drew attention because they seemed comfortable in places once thought too extreme for vertebrates. Again, an old boundary moved, and where fish exist, predatory dynamics deepen. Mobility changes things. Ambush becomes possible. Pursuit enters the system, even if often subtle. Then there are octopuses. Not everywhere, not always central, but enough to stir fascination, because the idea of an octopus moving through hydrothermal terrain feels almost inevitable once imagined. Intelligence, flexibility, predation. A hunter in a landscape of chimneys. Even brief observations seemed enough to remind researchers the vents do not exclude complexity, they generate it, and predation is part of that complexity. There is something important in this, because without predators, vent communities might be mistaken for chemical gardens alone, static arrangements around energy sources. But predators reveal tension, risk, response, behavior shaped by threat, life not merely feeding, but avoiding being fed upon. That makes ecosystems feel complete, more whole. Some scientists became interested in how predation might shape vent community structure. Which species dominate? Where organisms position themselves? How behaviors change? Whether certain dense aggregations offer protection? Whether proximity to harsh vent conditions sometimes creates refuge from predators less tolerant of extremes. A remarkable thought. That danger itself, heat, chemistry, instability, may sometimes shield the vulnerable, as if harshness can become sanctuary. Again, hydrothermal systems invert expectation. Even hunting here may be shaped by invisible gradients. A predator cannot ignore heat boundaries, cannot simply pursue anywhere. The environment itself constrains pursuit, shapes attack, defines where predator and prey can meet. In that sense, the vent field is never just background. It participates. The habitat itself enters the struggle. There is also the matter of scale. Some predation may be small, almost microscopic. Microbial interactions, tiny consumers, grazing bacterial films, minute worlds within larger ones. Because at vents, ecology stacks layer upon layer, visible and invisible, large and small, and every layer may include consumption. That truth can seem harsh, but it is also ordinary. Predation is not disorder, it is process, part of how energy moves, part of how systems persist. Even in darkness, perhaps especially in darkness, there is a temptation, when speaking of hydrothermal vents, to make them too extraordinary, to feel ecological in familiar ways, to treat them as exceptions to ordinary life. But predators remind us something almost opposite may be true. These systems are strange, yes, alien in appearance, yes, but they are also ecosystems in the deep sense, with competition, consumption, risk, death, renewal, not outside nature, but profoundly within it. And perhaps that is more wondrous, that even in places once imagined barren, the old patterns return. Life feeds, life is fed upon, energy passes onward. The grammar of ecology persists far below sunlight, where black smokers breathe into dark water. Crabs still hunt among mineral towers. Fish move through shadows beyond the plumes. A predator waits where shrimp gather too close. And somewhere in the slow current, one living thing senses another, because even here, at the edge of heat, in a world built on chemistry, the ancient law remains. Where there is abundance, something hunts. Life that exists nowhere else. One of the quietest shocks in hydrothermal vent science did not come from heat or chemistry, or even from the strange appearance of the creatures themselves. It came from a deeper realization. Some of these organisms existed nowhere else, not merely unusual, not merely rare, endemic, bound to vent systems, restricted to habitats so specialized that outside them they may have no world at all. That is a different kind of wonder and a different kind of fragility, because when scientists first began cataloging vent species, many assumed at least some creatures might prove to be variants of already known deep-sea life, modified perhaps, specialized, but connected to broader communities. Sometimes that was partly true, but often the vent world offered lineages astonishingly distinct, animals shaped by evolutionary pathways, so tied to chemical habitats. They seemed almost like biological signatures of the vents themselves. Consider again Riftia pachyptila, its dependence on symbiotic bacteria, its physiology, its ecological placement. This was not a creature likely wandering far beyond vent-influenced worlds. Its life was written around chemistry too specific to ignore. Or consider the remarkable Pompeii worm associated with vent habitats so extreme it became almost legendary among deep-sea researchers. Its very existence seemed to press against assumptions about where complex life could persist, and yet it existed not broadly across ordinary ocean floors, but here at vents there were mussels, shrimp, crabs, microbial communities, entire assemblages whose identities made sense only when understood through hydrothermal conditions that mattered. Because endemism changes how one sees a place. A habitat is no longer simply somewhere organisms happen to live. It becomes irreplaceable. Lose it, and you may lose what lives only there. No substitute, no alternate refuge. That idea began shaping conservation concerns long before they entered public discussion, especially as deep-sea mining proposals raised alarms, because vent sulfide deposits attractive to industry are also habitats, and endemic systems do not easily relocate. Some scientists began speaking of vent fields almost as evolutionary islands, a comparison with depth. Like isolated islands at the surface, separated populations may diverge, adapt, become distinct. Only here the islands are not land. They are chemical oases, scattered along fractured ridges, separated by dark expanses of unsuitable seafloor, connected only, perhaps, by drifting larvae and improbable dispersal, an archipelago in darkness. It was a powerful idea, and it helped explain something else. Why vent communities in different regions could differ markedly. Species at the East Pacific Rise might not mirror those in Atlantic systems. Biogeography existed even here. Patterns, provinces, boundaries, as if the deep sea too held its own invisible continents. This fascinated evolutionary biologists because isolation drives invention, and hydrothermal vents, through instability and separation, may have encouraged it. Temporary habitats, harsh conditions, dispersal challenges, strong selective pressures, a remarkable recipe for evolutionary distinctiveness. And perhaps that is why vent biodiversity can feel so disproportionate to the size of the habitats themselves. These are not broad, shallow seas, not continents of coral reef. They are comparatively limited places, and yet what they contain can be astonishing, as though extremes sometimes concentrate novelty. There is something almost moving in the thought that in darkness, beyond sunlight, life did not merely persist. It diversified, invented, specialized, became singular, not despite harshness, but partly because of it. That may be one of the deepest lessons of hydrothermal vents. Extremity does not always impoverish life. Sometimes it shapes forms found nowhere else. Still, endemism carries vulnerability. If a vent dies, if networks are broken, if habitats are damaged faster than species can disperse, loss may be permanent, because some organisms have no second home. That lends the vent world a quiet urgency. Wonder and risk intertwined, as they often are in places humans discover late. And perhaps there is something humbling here too, that some of Earth's most unique living forms evolved in places humans only recently learned existed, unseen through most of human history, yet flourishing all the while. It reminds us how incomplete our maps of life once were, and perhaps still are. Far below the surface, where chimneys rise from fractured crust, there are creatures whose whole existence belongs to those hidden worlds. They do not migrate to sunlit seas. They do not belong to coral reefs. They do not wait in familiar oceans beyond the vents. They belong there to heat gradients, to mineral towers, to chemistry rising from Earth and nowhere else, which means that in the darkness around hydrothermal vents, human beings did not merely find strange life. They found living forms the planet had been keeping for itself. Alvin and the Age of Deep Submersibles. Long before hydrothermal vents entered public imagination, before black smokers became icons, before giant tube worms appeared in documentaries, there was a quieter story unfolding. A story not about the creatures, but about how humans reached them at all. Because none of these discoveries happened from the surface. No ship drifting above could simply look down and see chimneys rising in darkness. The deep sea keeps itself hidden, and to enter that hidden world, human beings had to build vessels willing to descend where human bodies alone could not go. Among those vessels, one name returns again and again: DSV Alvin. There is something almost modest about Alvin compared with the scale of what it helped reveal. It is small, cramped, practical, not grand in appearance, and yet few machines have altered human understanding of the deep ocean more. Launched in the 1960s, Alvin existed before hydrothermal vents were known. Its early missions carried different ambitions: deep sea science, geology, exploration, recovery operations. It would later play roles in investigations reaching far beyond vents. But in the story of hydrothermal systems, Alvin became something like a threshold because it took people there, inside, in person, that mattered. There is a difference between sensing something remotely and sitting in a pressure sphere, watching it appear in your lights. A profound difference. The interior of Alvin has often been described as intimate to the point of discomfort. 3 people, typically, pressed into a small sphere, surrounded by instruments, limited space to move, hours descending, hours below, hours ascending again. No easy exit, no wide windows, only viewports, small portals into immense darkness. Imagine the psychology of that. Dropping through black water for hours, knowing the ocean above grows heavier with every meter, knowing the pressure outside would crush ordinary structures instantly, knowing you depend on steel, engineering, and judgment. And then, after long descent, lights reveal the seafloor, and perhaps a black smoker rising, a forest of Riftia pachiptila swaying in darkness. To witness that from inside a sphere barely large enough to sit in must have felt almost unreal. Some scientists later described deep submersible dives not merely as research, but as experience, immersive in the truest sense, because the deep sea does not appear as an abstract graph. Inside Alvin, it surrounds you. Its silence, its darkness, its scale, even its slowness, all become immediate. And Alvin made repeated immediacy possible. That changed science, because repeated dives mean revisiting sites, comparing change, observing patterns, testing ideas. Not a single revelation, but sustained exploration. That is how hydrothermal vents became understood as systems, not curiosities. Alvin helped make that transition. It also shaped how humans imagined exploration itself. There is something almost old-fashioned, in the best sense, about crude submersibles, human beings physically going somewhere difficult to reach, not sending only instruments, going. A continuity, perhaps, with older exploration, ships crossing unknown seas, polar expeditions, desert crossings. Only here, the frontier lay downward and colder and darker. Of course, Alvin was not alone forever. Other deep submergence vehicles emerged. Technology advanced, capabilities expanded, but Alvin became emblematic because it arrived at the right moment and kept arriving again and again. There were risks, always. Deep ocean exploration has never been casual. Systems fail, conditions change, the environment forgives little. Every descent carries that truth quietly. Perhaps every crew feels it, which may be part of why discoveries made from such dives carry a certain weight. They were not made from comfort. They were earned through descent. There is another reason Alvin matters. Presence changes perception. Scientists seeing vent life firsthand often noticed things not easily reduced to data alone: spatial relationships, movement, unexpected behaviors, the feel of a place, subtle impressions that later shape questions instruments alone may not suggest. This is harder to measure, but not trivial. Exploration has always involved noticing, and Alvin enabled noticing. It also gave the public something powerful, a human point of entry. People could imagine 3 individuals inside a small submersible descending into blackness. That is a story the mind can hold, and through it, hydrothermal vents became less abstract, more real. The age of deep submersibles did not only discover strange world, it changed the relationship between humans and the abyss, made the deep less unreachable, though never ordinary. Far below the surface, long after sunlight vanishes, a small sphere descends. Its lights cut through black water. Its occupants wait, and somewhere ahead, chimneys begin appearing in the dark. The earth breathing below, and inside that fragile vessel, human beings, for a few suspended hours, enter a world they were never built to survive, but somehow learned to visit. ROVs and robots. For all the wonder of crude descents, there were limits. Human beings can only remain below so long. Submersibles are small. Dive time is precious. Risk is never absent. And some places are too deep, too unstable, or too demanding even for repeated human presence. The ocean, as always, was larger than direct access, and so another age of exploration grew beside the age of submersibles, not replacing it, expanding it. The age of robots, of remotely operated vehicles, ROVs, machines lowered into darkness on long tethers, connected to ships above, piloted not from inside a pressure sphere, but through cameras, controls, and patience. At first glance, something seems lost. No human physically present in the deep. No one looking through a viewport. Only monitors, joysticks, fiber optic lines carrying images upward. And yet, something immense was gained. Duration, reach, precision, persistence. ROVs could stay where people could not. They could return again and again. they could watch, and in science, watching over time changes everything. Vehicles such as Jason and others helped transform hydrothermal research, not merely by reaching vents, but by studying them with a kind of patience difficult in shorter crude dives. A robot could hover near a chimney, record shimmering vent flow, watch organisms over long intervals, return to the same structures, see what changed. That last part mattered deeply because hydrothermal vents are dynamic, and dynamic places reveal themselves through repeated observation, not single glimpses. Through robots, chimneys could be mapped in extraordinary detail. Vent fields surveyed, mineral structures measured, high-resolution imagery built into mosaics. Places once encountered as isolated scenes in submersible lights became landscapes. Cartography entered the abyss. The hidden world gained geography. That was no small shift. To map something is, in a sense, to begin knowing how it fits. ROVs also brought touch, not human touch, mechanical touch, manipulator arms reaching toward chimneys, collecting mineral samples, gathering organisms, positioning instruments, placing sensors where no diver could go. There is something quietly astonishing in a machine arm, guided from a ship at the surface, touching a vent thousands of meters below. Human intention extended through cable into darkness, almost like a long nervous system. Ship above, robot below, thought moving between them. And then there was video. Perhaps this changed public imagination almost as much as science, because suddenly hydrothermal vents could be seen not only by a few researchers in a pressure sphere, but by many. Recorded, shared, studied, returned to. The deep sea became visual in a new way, and once visible, it entered culture more fully. People could watch black smokers venting, see riftia pachiptila forests sway, see shrimp crowding near shimmering hot water, see the strange stillness of a living vent field. Images carry their own power, and robots made images abundant. There were other advantages. Depth. Some regions lie beyond routine reach of crewed vehicles. Robots extended exploration farther, safer, often more flexibly. And as technology advanced, so did capability. Better cameras, better navigation, better sampling, greater autonomy. In some systems, the machines themselves evolve almost as though exploration had its own ecology of tools adapting to the frontier. And yet, there remained something philosophically interesting here. ROVs changed the human relationship to discovery. They made presence mediated, not absent, but mediated. The scientist may not physically descend, yet still sees, still guides, still decides. Exploration became distributed between human mind and machine body, a partnership that seems fitting somehow in a story where symbiosis appears so often. There were limits too. Cables constrain. Weather above can affect work below. Robots can fail. Mechanical systems can become trapped. The deep resists mastery. Even now, perhaps, especially now, but still, ROVs opened something irreversible. Continuous observation, long-term monitoring, a way to study vents, not only as discoveries, but as changing worlds. That distinction matters. Discovery reveals existence. Observation reveals behavior, and behavior is where much understanding lives. far below the surface, while a ship drifts above in ordinary daylight. A robot may hover beside a black smoker, its cameras watching dark plumes rise, its instruments listening to a vent field breathe, its manipulator arm reaching toward mineral towers built in darkness. No human sits there, and yet human curiosity is present, extended through wire, through signal, through machine, and in the silent deep, robots began doing something remarkable, not merely helping humans find hidden worlds, but helping them stay long enough to watch those worlds change. Eruptions on the seafloor. For a long time, even after hydrothermal vents were discovered, it was possible to think of them as dramatic, but still relatively stable. Chimneys growing, fluids venting, communities gathering, a kind of restless equilibrium. Then scientists began witnessing something more sudden, something harder to fit into that calmer picture. The seafloor could erupt, not only in the distant geologic sense, but in events abrupt enough to transform vent worlds within human observation. That realization changed everything, because it meant hydrothermal ecosystems were not simply shaped by slow processes. They could be interrupted, buried, remade, sometimes almost overnight. The connection between vents and volcanism had always been understood in theory. Mid-ocean ridges are tectonic boundaries. New crust forms there, magma moves. But theory is one thing. Watching evidence of recent eruption alter a known vent field is another, and that began happening. Sometimes researchers returned to sites and found familiar features gone. Chimneys collapsed, terrain changed, fresh lava where living communities had been, a place once inhabited, erased or seeming erased. Some of the most influential observations came at places associated with the East Pacific Rise, where eruptive events and their aftermath revealed how rapidly deep-sea landscapes can change. What looked fixed was not. A vent field could be transformed by molten rock emerging beneath kilometers of ocean. It is a difficult image to hold, because people tend to imagine volcanoes as mountains, ash columns, surface violence. But here, the eruption happens in darkness, under crushing pressure, invisible to the ordinary world, and yet no less real, no less transformative. Some eruptions altered fluid pathways. Old vents ceased, new ones opened. Hydrothermal circulation reorganized. The Earth, in effect, rewired its own hidden plumbing, and ecosystems felt the consequences immediately. Where Riftia Pachytela colonies had stood, there might be burial, loss, silence. At least for a time, there was something almost brutal in that. Years of biological growth erased in geological moments. And yet, this was not the whole story, because scientists also witnessed return, recovery, colonization, new life appearing in disturbed terrain. At first, often microbial pioneers, then other organisms, succession unfolding. The story did not end with lava. Sometimes it began there again. That may be one of the most remarkable lessons seafloor eruptions offered. Catastrophe and renewal were intertwined. The destruction of one vent system could create conditions for another. An ending could open habitat. A burial could precede colonization. In darkness, ecology and geology braided together. Some researchers came to see eruptions almost as pulse events, resets in a larger rhythm, not anomalies outside the system, but part of how the system works. That is a profound shift. It means disturbance is not merely something life at vents endures. It may be something around which life has evolved. Adaptation not despite catastrophe, but with catastrophe assumed. That idea has weight because it suggests instability is not exception, it is background, the ordinary condition. There were also practical scientific consequences. Repeated monitoring became far more important because without revisits, these transformations might go unseen. A vent field mapped once could mislead if treated as permanent. Time entered interpretation, and once again, robots and submersibles together became essential. Watching before, during where possible, and after. Some of the most moving images in vent science are not only of discovery, but of return. Seeing life reappear where lava once seemed to have ended everything. That carries emotional force, even in technical research, because humans respond to renewal, even under the sea, perhaps especially there. And there is something else. Seafloor eruptions remind us the deep ocean is not passive background to life. It is active participant. The habitat does not merely host organisms. It erupts beneath them, bursts through them, recreates the stage while the play continues. That is rare to grasp in ordinary ecosystems. At vents, it is impossible to ignore. Far below the waves, where no one hears the fracture open, magma may rise through young ocean crust. Lava may spill across a vent field. A black smoker may fall. A living colony may vanish beneath fresh rock. And yet, months or years later, small pioneers may return. Then others. Then perhaps a new community. Different or familiar. The earth opens. The earth burns. The earth cools. Life comes back. And in that hidden cycle, deep beneath sunlight, the seafloor reveals something both severe and strangely hopeful. Even in places built on fracture, beginnings can rise after fire. The threat of deep-sea mining. For decades, hydrothermal vents were discussed mainly as places of discovery, geological wonders, biological frontiers, windows into origins. Few imagined they might also become contested ground. But as science revealed something else about black smokers, that they can contain rich deposits of copper, zinc, gold, silver, and other metals, another interest appeared, industrial interest, and with it, a difficult question. If the seafloor holds valuable mineral deposits, will humans try to mine the very places they only recently learned existed? That question is no longer theoretical. It has entered policy, debate, concern, because what scientists call seafloor massive sulfide deposits, formed in part through hydrothermal processes, can attract attention precisely because black smokers are not only ecosystems, they are also mineral structures. To geology and industry, those facts can point in different directions. To one, wonder. To another, resource. Sometimes both. And where those meanings overlap, conflict often begins. Some proposals have imagined machines operating on the seafloor, cutting sulfide structures, collecting material, processing or lifting ore upward. Industrial systems in places once visited mainly by submersibles and robots of science. Even the image feels jarring. A mining machine where Riftia, Pashipila colonies may stand. Noise where dark water once held only currents. Disturbance where fragile chemical habitats persist. And this is where concern sharpens, because hydrothermal vent ecosystems are not easily replaced. Some species are endemic, as we have seen. Some habitats may recover slowly, some perhaps unpredictably. Some losses could be permanent, especially if connectivity among vent fields is disrupted. That point has become central. It is not only one chimney or one site, but networks, dispersal pathways, hidden ecological relationships, still only partly understood. Can mining disturb them without lasting damage? Some ask yes, perhaps with caution. Many scientists urge far greater uncertainty, and uncertainty itself matters because ignorance is not safety. Not in fragile systems. There are other concerns. Sediment plumes. Though vents are already dynamic places, industrial disturbance may spread effects beyond the immediate extraction site. Noise may alter organisms. Chemical conditions may shift. Microbial communities, so foundational, yet often least visible, could be disrupted in ways difficult to predict. And prediction is hard enough in shallow ecosystems, harder still in worlds humans have barely studied. That fact haunts much of this discussion. How can one manage what one scarcely knows? It is a simple question and not easily answered. Some researchers argue active hydrothermal vents should be treated with strong protection. Others distinguish between active systems and inactive sulfide deposits, though even their debate remains. Regulatory discussions continue. International bodies have been drawn into these questions, and still no easy consensus settles the matter. Perhaps because the issue is larger than mining. It is about how humanity behaves when discovery becomes economically tempting. A very old pattern repeated in forests, rivers, reefs, now perhaps the abyss. That repetition gives the debate a moral undertone, whether one intends it or not, because hydrothermal vents are not places humans depended on for civilization. They are places humans stumbled upon late, places astonishing in their novelty, and almost immediately questions of extraction followed. There is something revealing in that, and perhaps uncomfortable. Yet, the discussion is not only alarm, it has also produced serious science. Calls for baseline research, monitoring, precaution, protection before exploitation. Some of the most important work may lie there, in deciding whether knowledge can arrive before damage, whether wonder can slow appetite. That remains open, and perhaps this late-night story should leave it open, because certainty would be false. The future of these places is not fully written, but the question now exists and cannot be ignored. Far below the surface, where black smokers still rise in darkness, metal-rich chimneys continue forming as they have for ages. Tube worms sway, shrimp gather, microbes feed. The earth keeps building structures no human made, and somewhere far above, humans debate whether those structures are habitats or deposits, worlds or ore. The answer may shape what remains in the dark, because for the first time in the story of hydrothermal vents, the danger is not only heat or eruption or instability from the earth below. It may come from above. Vents and alien oceans. Long before hydrothermal vents were discovered on Earth, the idea of life beyond Earth often leaned towards sunlight, another planet, perhaps with air, liquid water on a surface, clouds, maybe something like oceans under a sky. The imagination was, in a sense, terrestrial. It borrowed from what was familiar, but hydrothermal vents changed that quietly at first, then profoundly, because once scientists understood life could thrive without sunlight, fed instead by chemistry rising from a planet's interior, the map of where life might exist widened, perhaps dramatically. Places once dismissed as too dark, too cold, too hidden, no longer seemed automatically empty. And nowhere did that shift matter more than in thinking about ocean worlds, worlds where water may exist, not at the surface, but beneath ice, hidden seas, dark seas, seas no wind has touched. The most famous of these is Europa. For decades, Europa stirred fascination. Its surface, bright, fractured ice, a shell crossed by lines and scars, beautiful, cold, seemingly barren, and yet evidence grew that beneath that ice, an ocean may exist, a vast one, perhaps global, perhaps in contact with rocky interior material. And if water meets rock, scientists ask almost automatically now, could hydrothermal activity exist there too? That question would have sounded more speculative before 1977. After hydrothermal vents, it sounded grounded, possible. Because if Earth's vents show chemistry can support ecosystems in darkness, then a hidden European ocean no longer seems lifeless by default. It becomes a place one can ask about seriously. And then there is Enceladus, perhaps even more haunting in some ways, because Enceladus did not only invite speculation, it surprised. Plumes of water-rich material erupting from fractures near its south polar region, material escaping into space as though the moon itself were exhaling. There was something strangely reminiscent, at least metaphorically, of Earth vent systems, a world showing signs of internal activity, water, chemistry, energy sources, enough to provoke a difficult thought. Could something be happening below that resembles, in some distant way, hydrothermal interactions? Scientists are careful, as they should be. Possibility is not proof. Analogy is not evidence. No one has seen an alien vent. No one has found extraterrestrial life. That remains true and important. But what changed is the seriousness of the question. Hydrothermal vents on Earth gave astrobiology a precedent, a real example, not fantasy, a model that matters enormously, because science often advances not by proving distant things directly, but by showing what is possible somewhere known. Earth became that somewhere. Its deep ocean became argument, and the implications widened beyond Europa and Enceladus, other icy worlds, hidden oceans perhaps elsewhere, even ancient Mars. In some speculative scenarios involving water-rock chemistry, the map kept growing, all because life at Earth's vents made the universe feel chemically more interesting, less dependent on sunlight, more open to hidden habitability. There is something almost poetic in that. that by descending into Earth's deepest darkness, humans expanded how they imagine life among the stars. The road outward passed downward, and perhaps that is why hydrothermal vents carry such unusual symbolic weight. They belong equally to oceanography and to dreams of alien biology. Few discoveries do that. Most stay in their disciplines. Vents escaped theirs because they touched a universal question. Are we alone? Not by answering it, but by making one old reason for saying probably yes less secure. Darkness, it turned out, does not mean dead, and that changes thought, perhaps permanently. Still, one should be humble. Alien oceans remain unseen in the way Earth's deep sea can be seen. Much remains inference. Much remains hope disciplined by evidence. That is honest, and honesty belongs in wonder. But even honest wonder can be vast. Far below the ice of a distant moon, there may be water touching rock. There may be chemistry. There may be gradients. Perhaps somewhere, something living. Or perhaps not. We do not yet know. But we ask because at the bottom of Earth's ocean, black smokers taught us such questions are no longer unreasonable. And so, in the silence beneath alien ice, scientists sometimes imagine something familiar. A dark seafloor, a rising plume, mineral towers in hidden water, and perhaps very far from Earth, another world breathing below. Could life begin like this? Once hydrothermal vents began reshaping ideas about where life might exist, it was almost inevitable. The question would turn back inward again, not toward alien oceans this time, but toward Earth, toward the oldest mystery. Could life itself begin in places like this? Not merely survive here, not merely adapt here, begin here. It is a larger question than any one discovery can answer, and hydrothermal vents did not solve it, but they changed how seriously one version of the question could be asked. Because before vents entered this conversation, some origin theories seemed easier to imagine. Surface chemistry, warm shallows, lightning, sunlit cycles. Hydrothermal systems were, at best, peripheral in many popular accounts. Then the deep ocean complicated that, because vents offered something origin theories need. Not magic, but process. Persistent process. Energy flowing continuously. Chemical disequilibrium sustained. Minerals available. Boundaries where reactions might concentrate rather than disperse. Not proof of beginnings, but ingredients for thought. And in origin research, ingredients matter. Some scientists focused on mineral pores, microscopic compartments within vent structures, tiny natural chambers, places where molecules might gather, interact repeatedly, perhaps form more complex arrangements. Because one difficulty in origin scenarios is dilution. Oceans are vast. Molecules disperse, but compartments change that. They hold things together long enough, perhaps, for chemistry to do more. There was something compelling in the simplicity that rocks themselves through structure alone might assist prebiotic organization. Others focused on gradients, particularly chemical differences across boundaries, because living cells today rely on gradients. Energy, in many cases, is managed through them. Could something analogous have roots in ancient geochemical settings? vents. The question was irresistible and remains so. Some looked especially toward alkaline hydrothermal systems, often associated conceptually with sites like Lost City Hydrothermal Field, because such environments seem to offer not only chemistry but relative persistence. Time matters in beginnings, repeated opportunities matter, and hydrothermal systems seemed to offer both. Still, science here demands caution. No one watched life begin. No vent has yielded a preserved record saying, "Here it happened." Origin of life research remains inferential, experimental, fragmentary. There are competing models. Surface scenarios remain serious. Hybrid ideas exist. Debate is not a flaw, it is the field. And that uncertainty matters, because romanticizing vents as if they solved the origin of life would be false. They did not. What they did was harder, and perhaps more important. They made certain questions scientifically richer, more plausible, more detailed. They gave origin theories new terrain. That is real and enough. There is also something conceptually beautiful in vent-based thinking, because it shifts the image of beginnings, not life emerging in dramatic lightning-struck spectacle, but perhaps in slow repetition, gradients sustained over immense time, molecules meeting again and again, failure, then persistence, then maybe something holding, then copying, then evolution. Far later, a quieter beginning, less theatrical, more patient. That vision carries a kind of deep-time humility. Life not as sudden miracle, but as long negotiation between chemistry and possibility. Some researchers have even suggested the boundary between geochemistry and early biology may once have been less sharp than we assume, that what we call living emerged gradually from systems already doing something lifelike in limited ways. Again, debated, unresolved, but intellectually profound, because it asks whether life did not begin as an object, but as transition. And hydrothermal vents seem, to some minds, good places to think about transitions, where water meets rock, where heat meets cold, where gradients meet structure, where one state becomes another. Vents are boundary places, and beginnings often belong to boundaries. There is also an emotional undertone, difficult to ignore. If life began, even partly, in darkness around hydrothermal chemistry, then every living thing traces, however distantly, to hidden places no sunlight reached. That is a startling thought. That forests, birds, whales, human memory, human grief, human music all may stand at the far end of chemistry once moving through fractured rock. It is almost too large a thought to hold, and perhaps that is why it lingers, not because it is proven, but because it feels at once strange and strangely coherent. Far below the ocean, hot fluids still rise through chimneys, minerals still precipitate, gradients still persist. The earth is still conducting chemistry as it has for ages, and somewhere in that ongoing process, scientists still look for echoes, not of creatures alive now, but of something earlier, something before cells, before evolution had names, before life was recognizably life. And in the silent dark near vents where the earth breathes, the question remains: could life begin like this? No final answer yet, only the possibility, still rising like heat through water from below. What the vents still hide. After decades of discovery, it can be tempting to imagine hydrothermal vents as a frontier largely mapped, catalogued, understood, known. Black smokers found, lost city described, species named, theories debated, robots deployed. Perhaps one might think the great surprises have mostly happened, but the deeper truth may be almost the opposite. Much may still be hidden because the seafloor is immense. Mid-ocean ridges alone stretch across the planet in lengths so vast they are often described as Earth's longest mountain system, most of it unseen by human eyes, much of it only coarsely mapped, some not closely explored at all. And hydrothermal activity may occur in places no one has visited. That fact alone should slow any sense of completion. We may know the phenomenon, but not its full extent, not even close. How many vent fields remain undiscovered? The honest answer is uncertain. Perhaps many. That uncertainty is not failure, it is frontier. Some discoveries in recent decades have come precisely because scientists looked in places once thought unlikely. Different ridge systems, back arc basins, unexpected geologic settings. Again and again, the ocean has shown a talent for exceeding assumptions. That pattern itself suggests caution. If surprise has been recurrent, why assume it has ended? And the hidden may not be only places. It may be organisms, unknown species, microbial lineages, scarcely characterized, life forms difficult to culture, behaviors never observed, entire ecological interactions only inferred. The visible animals, Riftia, Pachiptila, shrimp, crabs, capture imagination. But much of vent biology may remain microscopic, and microbial worlds are often where the deepest unknowns lie. Invisible does not mean simple, often the reverse. There may be metabolisms not yet fully understood, relationships not yet recognized, biochemistry with implications reaching beyond marine ecology. The hidden can be conceptual too, not just geographic. Some mysteries concern processes. How exactly do certain vent systems initiate? How stable are some over-geologic timescales? How do organisms disperse across great deep-sea distances? How resilient are communities to disturbance? Questions remain open, and open questions are a form of hiddenness. They mark what discovery has not yet entered. Technology keeps widening that edge. Autonomous vehicles, better mapping, long-term sensors, genetic methods. Every tool seems to reveal more, and often reveal how much was missed before. There is a paradox in mature science. The better we look, the larger ignorance sometimes appears. Hydrothermal research has often carried that paradox, knowledge expanding and mystery expanding with it. There is something healthy in that, because it keeps wonder honest, not naive wonder, but informed wonder, the kind rooted in knowing how incomplete the map remains. Some researchers suspect there may be vent-like systems associated with geological settings not yet adequately searched. Others think certain types of hydrothermal activity may be undercounted simply because they are harder to detect. The ocean keeps its secrets, partly through scale, partly through difficulty, and partly because we have only begun asking some questions. That too matters. Discovery is shaped by what one knows to look for, And what if there are phenomena no one yet knows to seek? That possibility is difficult to dismiss. History encourages humility. Before 1977, many did not imagine hydrothermal ecosystems at all. Then they were found. If something equally surprising waits still, would we recognize it immediately? Perhaps not. That thought lingers, and perhaps it should, because frontiers are rarely exhausted when they still produce astonishment. Far below the surface, along ridges stretching through darkness, there may be chimneys no light has touched, vent fields no submersible has approached, species no one has named, microbial worlds no laboratory has understood. The Earth may still be building hidden ecosystems in silence, as it did long before humans arrived. And perhaps somewhere in an unmapped fracture, hot fluid rises now through young ocean crust. Minerals precipitate, a chimney grows, creatures gather, a whole living world begins its ordinary existence, unknown to us, still hidden, still unrecorded, still part of the planet, whether or not anyone sees it, which may be the deepest mystery of all, that the hydrothermal vents we know may be only the ones the Earth has allowed us to notice. The last descent. At the end of long exploration, there is often a temptation to conclude with certainty, to gather discoveries into a final statement, to say what hydrothermal vents mean, to summarize, to close the book. But some subjects resist that, and perhaps hydrothermal vents do, because they do not feel like a mystery solved. They feel like a mystery entered. And so perhaps the proper ending is not conclusion, but return. One more descent, a final, imagined descent into the dark. The submersible drops slowly. Perhaps again, it is DSV Alvin, or perhaps only the idea of it. A small sphere entering black water above. Sunlight fades, then disappears. The ocean grows cold, silent. Pressure gathers invisibly around the hull. Hours pass, nothing outside the viewport but darkness. Then the seafloor, basalt, sediment, broken volcanic stone, and farther ahead, something rising, a chimney, then another, then a field of them, black smokers breathing into the sea. There are the tube worms again, Riftia pachyptilla, swaying slowly, shrimp gathering near shimmering water, mineral plumes rising, the earth breathing through fractures, just as before. And yet somehow, after knowing more, the scene feels larger, not smaller, because now each thing carries layers. The chimneys are geology and origin theory, and possible echoes of alien oceans. The worms are animals and symbiosis and redefinitions of life. The dark water is ocean and frontier, and perhaps reminder that the world remains far less fully known than humans often pretend. The submersible drifts, nothing hurried, only currents moving, particles drifting like underwater dust, and one can imagine sitting there in silence, not taking samples, not measuring, only watching. There is value in that too, in letting a place remain partly itself, untranslated. Somewhere in the black water beyond the lights, a predator moves. Somewhere a vent field undiscovered may lie beyond mapped ridges. Somewhere beneath ice, on a distant moon, perhaps another ocean waits, or perhaps not. Uncertainty remains, and perhaps that is part of the beauty, because certainty ends wonder, more quickly than mystery does. Hydrothermal vents have given science extraordinary things: new biology, new geology, new questions about origins, new ways of imagining life beyond Earth. That is already much, more than much. And yet, perhaps their deepest gift has been subtler. They reminded us how wrong human assumptions can be, how much can exist beyond expectation, how often the hidden world is stranger than the visible one. That is not only scientific, it is philosophical, almost spiritual in its humility. At the bottom of the ocean, where sunlight never arrives, the Earth has been building chimneys, circulating mineral, feeding ecosystems, perhaps for immense spans of time, all while human history unfolded unaware. Empires rose, languages changed, religions formed, wars were fought, music was written, and below all that, the vents kept breathing, unnoticed. There is something calming in that thought. The planet is deeper than our attention, older than our urgency, more patient than our noise. The submersible turns slowly. Its lights sweep once more across the chimneys, then begin to rise. The ascent starts. Darkness closes again. The vent field disappears below, hidden once more. And perhaps that is fitting. Some places are not diminished by leaving them partly unseen. They become larger. Far below, the black smokers continue venting. The tube worms continue swaying. The Earth continues breathing through fractures in the dark, whether anyone watches or not. And as the last descent ends, one thought lingers, that at the bottom of the ocean, in silence, older than memory, human beings did not merely find strange life. They found a place where the planet itself still seems half creation, half secret,